Hello everyone and welcome to General Chemistry 2, lecture number 12, Equilibrium. This one's on LeChâtelier's principle or LeChâtelier's, don't quote me on my French pronunciation. This covers OpenStax sections 13.1 through 13.3. This topic specifically, LeChâtelier's principle, is mostly found in 13.3, but there's a little bit of review from the first two sections of chapter 13 here. So let's go ahead and get started. We're going to learn first about the reaction quotient. So in the previous lecture, we learned about the equilibrium constant Kc. So if I had a reaction CO plus Cl2 to form CoCl2, my Kc expression would be the concentration of my product, CoCl2, at equilibrium raised to the first power because of the coefficient of 1, divided by the concentration of CO at equilibrium times the concentration of Cl2 at equilibrium. So this tells you the ratio of products to reactants specifically at equilibrium. So these are only the concentrations at equilibrium. So there is only one value of K for a reaction at a given temperature. Now do remember that if you change the temperature, the K value will change, and we'll learn today how it can change, but strictly speaking, at a given temperature, there is only one K value. Now we're going to learn about something, again, this is called the reaction quotient. And the reaction quotient uses the variable, Q. It's defined by the letter Q here. So Q stands for the reaction quotient. You may see just Q, you may see it written as like QC or QP, depending on if you're talking about concentrations or pressures. If you just want to write Q, that's fine. Q is the same ratio, but measured at any point in time during the reaction, which is why here we can call it a snapshot in time. There are infinitely many different possible values of Q for a reaction at a given temperature because these concentrations can be measured at any point in time during the reaction, whereas K is equilibrium only. So what we can do here with this is we can compare the value of Q to the known value of K, and by doing so, we can figure out in what direction the reaction will proceed in order to reach equilibrium, essentially to make Q equal to K. So there are three to remember. If Q is less than K, this means we need to increase Q. And if we need to increase the value of Q, this means we need to make the number on top bigger, right? If I said to you, hey, Q is less than K, how do I get to equilibrium? If Q is less than K, obviously I need to make Q bigger. And if I want to make Q bigger, I should make this number on the top smaller, or make the number, or not smaller, make the number on top bigger, or make the numbers on the bottom smaller, or both, right? Both would work. So if I need to make the number on top here bigger, I need more products. Or if I'm trying to make the numbers on the bottom smaller, I need less reactant. Both of those things point towards the forward direction being favored. So the reaction would be favored in the forward direction. If Q is less than K, we need to increase Q by increasing the concentration of the products. And so the reaction is favored in the forward direction, or we could say the reaction would proceed towards the products or proceed in the forward direction. These are all different ways of phrasing it. They all generally mean the same thing. The second one is the easiest one. If Q is equal to K, the reaction is already at equilibrium. There's no change. We would not say the reaction is going to proceed in one direction or the other. And finally, if Q is greater than K. So if I said to you that this number right here is bigger than this number, and I want them to be the same, what do I need to do? Well, obviously, I need to make Q smaller. And if I want to make Q smaller, I either need to make this number on top smaller or make the numbers on the bottom bigger. So to decrease Q, I need to decrease the concentration of the products and increase the concentration of the reactants, which means the reaction would be favored, or the reverse reaction would be favored. Or we could say that the reaction would proceed in the reverse direction, from the right back to the left, to decrease the products and increase the reactants. So this is how Q can be very helpful to us. We can compare its value to K and then analyze that and determine which direction the reaction will proceed, left, right, or it's already at equilibrium. So let's practice with some reaction quotients. At a certain temperature, Kc equals 1.0 times 10 to the negative 13th for the below reaction. 2HF forms H2 plus F2. The following concentrations were measured at some point during the reaction. Is the reaction at equilibrium? So HF equals 0.500 molar, H2 equals 1.0 times 10 to the negative third molar, and F2 equals 4.00 times 10 to the negative third molar. If not at equilibrium, in which direction will the reaction proceed? So let's figure this out. We need to start by writing a Q expression. So I'm going to write my Q expression, and sorry, all the work appeared at once here because I couldn't animate the equation, but let's go one piece at a time. So I'm going to write my Q expression. So Q is going to be equal to the concentration of H2 times the concentration of F2 divided by the concentration of HF squared. So note that the coefficients become the exponents in the Q expression, just like they do with K. Then I can plug in the values given. So plug in 1.00 times 10 to the negative third for H2, 4.00 times 10 to the negative third for F2, and 0.5 for HF. So when I plug this in and solve, I get a value of 1.6 times 10 to the negative fifth. So right here, we were told that Kc equals 1.0 times 10 to the negative 13th. So we can see then that our Q value is bigger than our K value. The Q value is bigger than the K value, so the reaction is going to proceed left. This would be the correct answer here. The reaction proceeds left. We need to decrease the concentration of the products and increase the concentration of the reactant. We need to go left. Let's look at one more practice problem. Predict the direction the reaction will proceed at 448 degrees Celsius when the partial pressures of HI, H2, and I2 are 1.3, 2.1, and 1.7 atmospheres, respectively. So we're given the balanced chemical equation here. So now notice that we are given pressures instead. Everything's in the gas phase. So you can still write a K value for species in the gas phase. So we can say that Q, you can still write Q values, reaction quotient Q values for species that are in the gas phase and compare them with a Kp value. So Q equals the pressure of HI squared, so our only product on top, squared, divided by the pressure of H2 times the pressure of I2. Plug in the values given. So HI's pressure is 1.3, so I'll plug that in right there on top. H2's pressure is 2.1, so that gets plugged in on the bottom. I2's pressure is 1.7, plug that in on the bottom. When you plug in these values and solve, you should get a Q value of around 0.47. Notice this Q value is smaller than the K value, 0.47 versus 51. So if Q is smaller than K, we need to go to the right. We need to produce more products to increase the Q value. So your answer here would be the reaction would proceed to the right or in the forward direction. All right, now shifting from the reaction quotient to LeChâtelier's principle. So LeChâtelier's principle states if a system at equilibrium is disturbed, the system will shift in whichever direction, either forward or reverse, right or left, that will best serve to counteract the change. The reaction is going to shift to try and re-establish equilibrium. So if you change the conditions, the reaction will react to that because the reactions are always trying to get and stay at equilibrium. If you disturb the system by increasing the temperature or changing the volume or something like that, we're going to look at different changes here. You basically disturbed the equilibrium and the reaction is going to shift in one direction or the other to re-establish that equilibrium and counteract the change. So we can kind of think of it like we can imagine like a stick figure, like balancing on a board, or sometimes I'll use like a seesaw example. If you were ever played on seesaws when you were a kid, right? We can kind of use this as an analogy for a chemical reaction that has reached a state of equilibrium. What would happen if we suddenly added weight to one side of the board? How might we counteract that change? So, if I was on a seesaw and I added, let's say there was one person on this side and one person on this side, and then you added a second person to the left side, right? The seesaw would go like that, right? It would shift down where the left side would shift down, and the person on the right side might get stuck up top here. What do you do? How do you counteract that change? You need to add more weight to the right side. So that'd be an example of the reaction would shift right. And so I'll show you some examples here. Let's look at, generally speaking, and this system, N2O4 forms 2NO2. So we see that we've got some molecules of N2O4 and NO2. And what's happening here is we are showing the equilibrium being disturbed. So our reaction is at equilibrium. We're going to disturb that equilibrium by adding N2O4. So the system was at equilibrium, and then we disturb it by adding some extra reactant, by adding some extra N2O4. What happens when that equilibrium is disturbed? Well, now we have too much N2O4 in the system. So that extra N2O4 is going to start reacting with each other and forming NO2. And so the reaction shifts right. And so this is what I mean when I say you can kind of think about it like a seesaw analogy. So if I had a seesaw that looked like this, and so I've got my nice balanced equilibrium, what happened here is that I added some extra weight to the left side. So what happens when you add extra weight to the left side? The seesaw shifts like this. And so now my question is, I want to get back to this balanced state. Which side do I need to add more weight to? You need to add weight to the right side. So you would say then that the reaction shifts right. So whichever side you need to add more weight to, so to speak, in this seesaw or balancing board analogy, is the side that the reaction shifts to. So if you add extra reactant, the reaction is going to shift right and form more product in response to that disturbance in the equilibrium. What if we do the reverse? What if we take our equilibrium and we add some extra NO2? So we add some extra product into the mix here. Well, by adding the extra NO2, we've thrown off our ratio. There's too much NO2. Those extra NO2 molecules will begin reacting with one another. They'll begin colliding, as being shown here, and they'll form more N2O4. So when you add extra product, when you add something to the right side, the reaction shifts left in response. All right, so let's analyze a couple problems here. Here we have the chemical reaction N2 plus 3H2 forms 2NH3. What will happen if, while at equilibrium, we double the amount of H2, remove some N2, and add some NH3? I would encourage you to pause the video and see if you can come up with the correct answers here. All right, let's go over these. First, double the amount of H2. If we add a reactant, so if we double the amount of H2, we're adding some reactant. This is going to cause a shift to counteract the change. If we are adding to the left side, we're adding extra weight, so to speak, to the left side. If we want to reestablish equilibrium, if we want to rebalance, we need to, quote here, add extra weight to the right side, or basically the reaction will shift right. So by adding extra H2, the reaction will shift right in response. What if we remove some N2? So what if we take some N2 and pull it out here? So instead of adding weight to one side, it's like removing weight from one side. So if you remove some weight from the left side, so to speak, now the left side's too light. We need more weight on the left. We need more concentration, more specifically on the left side. So the reaction here is going to shift left. If you remove something from the left side, the reaction will shift left in an attempt to rebalance and reestablish that equilibrium. And finally, add NH3. If we add to the right side, once again, the reaction would shift left in response. So add to the left side, reaction shifts right. Remove from the left side, reaction shifts left. Add to the right side, reaction also shifts left. And then you can imagine then, if I said remove some NH3, if I removed from the right side, reaction would shift right in response. All right, now let's talk about volume and pressure effects. So the concentration effects are fairly easy and fairly straightforward to understand. What about volume and pressure effects? So using the same reaction, what will happen if, while at equilibrium, we increase the partial pressure of H2, have the volume of the reaction container, or double the size of the reaction container? And then final one is add an inert gas such as helium. Let's break these down. Increasing the partial pressure of H2, this is equivalent to adding more reactant. So if you increase the partial pressure of H2, you are just essentially adding more H2. If you're adding to the left side, the reaction will shift right in response. B and C, these ones are a little tricky. Have or double the volume of the reaction container. If you are dealing with a gas phase reaction, you need to consider what these do to the pressure. So if we decrease the volume, in this case, if we have the volume, this increases the pressure. So decreasing the volume increases the pressure. The system is going to try then and decrease the pressure to counteract that change. It doesn't like that it's been squeezed tighter than it should be, right? So decreasing the volume increases the pressure. The system doesn't like that. It makes it unstable. And so the system is going to try and counteract that increase in pressure by decreasing the pressure. It will do so by shifting to whichever side has fewer moles of gas. So if you decrease the volume, you are increasing the pressure. And if you increase the pressure, the system is going to shift to whichever side has fewer moles of gas. So we see in our reaction, we have 4 moles of gas on the left and 2 moles of gas on the right. So by having the volume, we increase the pressure. We are then going to shift right. So here, half the volume would cause this reaction to shift right towards the side with fewer moles of gas. The opposite is true if we double the volume. So if we double or increase the volume, increasing the volume decreases the pressure. In response, the system will try and increase the pressure by shifting to the side with more moles of gas. So if you double the volume or decrease the pressure, the reaction, or we could say the system, will shift towards the side with more moles of gas. And so the answer to letter C, doubling the volume, would shift this reaction left towards the side with 4 moles of gas. Finally, add an inert gas such as helium. This one is a little trickier. If the helium is added at constant pressure, so if the volume is allowed to expand, you would shift towards the side with more moles of gas. So basically, if we're saying the pressure is constant, so basically the volume is allowed to expand, then you will shift towards the side with more moles of gas. But if the helium is added at a constant volume, so if we're dealing with a rigid container here, the individual partial pressures of each gas in the reaction actually do not change significantly. So this comes from, if you need a review on this, I recommend checking out Chapter 8. This comes from a little bit of the definition of what an ideal gas is. It also deals with Dalton's law of partial pressures. We know that if we add more gas to a container, these gases, they don't really affect each other significantly. So on this type of question, if you were to be asked something like this, it should be specified in the question if that gas is being added at constant pressure, meaning volume expands. And if the volume expands, you would go back to the answer here given in letter C. But if that inert gas is being added at a constant volume, a rigid container, the individual partial pressures should not change. So Q doesn't change, meaning we would expect no change. There would be no shift here. All right, so that's how we handle volume changes. How about heat changes? So let's remind ourselves about endothermic reactions. So in an endothermic reaction with a positive delta H value, heat is taken in, right? Heat is being absorbed by the system. So in these types of problems, in these LeChâtelier's principle problems, it is very helpful to think of heat as a reactant if you are dealing with an endothermic reaction. If we raise the temperature of an endothermic reaction, this is equivalent to adding more reactant. This stress will cause the reaction to shift right or forward towards the product side. So again, if you have an endothermic reaction, think of the heat as a reactant. If we raise the temperature, we are effectively adding more heat, which means we are adding more reactant, and so the reaction would shift right in response. If we were to decrease the temperature, this is effectively removing heat. This is like removing a reactant, and so if you're removing a reactant, you're removing something from the left side. The reaction is going to shift left in response. The opposite is going to be true for an exothermic reaction. So in an exothermic reaction with a negative delta H, we think of heat as being given off, right? The system is releasing energy, or it's releasing heat to the surroundings. Therefore, it is helpful to think of heat as a product. So here, with this reaction, N2 plus 3H2 forms 2NH3. This reaction is exothermic. It releases heat. So let's think of heat as a product. Excuse me. If we raise the temperature of an exothermic reaction, this is equivalent to adding more product. And so if I'm adding product, I'm adding something to the right side. If I'm adding something to the right side, I need to shift left in response to rebalance the reaction. So adding heat to an exothermic reaction would cause, or raising the temperature, I should say, would cause the reaction to shift left. If I decrease the temperature, that's the equivalent of removing heat. So it's like removing something from the right side. If I'm removing something from the right side, I need to shift right in response to rebalance that equilibrium. All right, let's show this visually. So this is showing an endothermic reaction, N2O4 plus 2NO2. So N2O4 is colorless, whereas NO2 has a more of a brown color to it. So since this reaction is endothermic, that means we can think of heat like being a reactant. So if we cool this down, right, if we cool this reaction vessel down, so the reaction's occurring inside this vessel right here, if we cool it down, that's the equivalent of removing heat, right? Because heat's a reactant here. It's an endothermic reaction, heat's a reactant. If I cool it down, I lower the temperature. That's like removing something from the left side. And if I remove something from the left side, I remove a reactant. The reaction would shift left in response. So it shifts left towards the colorless N2O4. So when the reaction is nice and cool, the vessel appears clear because we have mostly N2O4 inside. If I increase the temperature of this reaction vessel, that's like adding heat. And so heat's a reactant. That's like adding something to the left side. If I add something to the left side, the reaction would shift right in response. So the reaction shifts right towards the NO2, and the NO2 has a brown color. And so we can visually see the shift occur from the increase in temperature here, shifting right towards the brown NO2 gas. All right, so let's review some temperature effects. So I would like you to pause the video and try these three problems. So given this reaction and this delta H value, what will happen if at equilibrium we raise the temperature by 60 Kelvin, remove 1.47 kilojoules of heat from the reaction container, and lower the temperature by 11.2 Kelvin. So pause the video and give these three problems a try. Okay, so here, this is an exothermic reaction. We have a negative delta H. It's an exothermic reaction. So since heat is given off or produced, we can consider heat to be a product. So if we add heat to the reaction, that is equivalent to adding more product. The reaction would run in reverse and shift left. Conversely, lowering the temperature would cause the reaction to shift right. So let me go back and explain the answers here then. Letter A here, raising the temperature. That's the equivalent of adding heat. The reaction is going to shift left in response. B and C are both the equivalent of removing heat. So that's like removing a product. So the answer to B and C would be to shift right here. All right, let's briefly talk about catalysts. So catalysts, important to note here, they do not change the ratio of products to reactants at equilibrium or at any other point in time. neither K nor Q is affected. Therefore, adding or removing a catalyst does not disturb a system at equilibrium, and it will not cause the reaction to shift. Remember from our kinetics lecture, lecture 9, catalysts will make a reaction get to equilibrium faster. They increase the rate of both the forward and the reverse reactions, but they do not disturb the equilibrium. They do not cause a reaction to shift. They simply help the reaction get to that equilibrium faster. All right, let's look at a few more challenging examples. Sometimes it's not so easy with LeChâtelier's principle. Determining the effect of a change depends on the reaction you are considering. Let's consider some other reactions and changes. So let's consider this reaction. What were to happen if I were to add more carbon to the reaction vessel? And second question, what were to happen if I were to halve the volume of the reaction container? Let's break down this first one. If I add more carbon, notice that carbon here is a solid, and solids don't appear in the expression for K or Q. So adding or removing carbon here actually should not have any effect on the equilibrium. Let's answer this second question. Having the volume doubles each of the partial pressures, but because there are equal numbers of moles of gas in the products as in the reactants, the value of Q is unaffected, so no change. You could work this math out for yourself to see here. So if you have the volume, we would expect no change because there's 2 moles of gas on the left and 2 moles of gas on the right. So keep in mind here the definitions of your equilibrium constants. Remember that solids and liquids don't appear. And also just make sure you're paying attention to the number of moles of gases if you're dealing with a volume or pressure effect. All right, this slide here summarizes everything we have reviewed on LeChâtelier's principle thus far. So if you'd like to review, I'd encourage you to pause the video now, but I'm going to keep on moving to a few more special examples. Let's look at a few tricky cases. So suppose I have the reaction NaOH, so sodium hydroxide, plus CO2, carbon dioxide, to form NaHCO3, which is sodium bicarbonate. While this system is at equilibrium, what happens if we A, add solid NaOH, B, add liquid water, or C, add HCl? Oh, sorry, I thought I had the answers explained here. Let me break down these examples. So first, what if I were to add solid NaOH? Well, I notice that solid NaOH does not appear in the equation, but I do know that NaOH, because it has a group 1 metal here, it has an alkaline metal here, this compound is highly soluble in water. So if I add solid NaOH to the system must have some sort of water component to it, given we have 2 aqueous compounds. If I add more solid NaOH, probably a good portion, if not all of that NaOH is going to dissolve. So adding solid NaOH is effectively adding more of this to the system. And if I add more aqueous NaOH to the system, the reaction should shift right in response. Now, if I add liquid water, this is going to change the concentration of all species. It is safe to assume here that some of this CO2 is probably dissolved given the state of matter here, right? CO2 can dissolve in water all the time. How will that affect Q? This one's a little bit more difficult. Now, I'm going to go ahead and assume everything here is a coefficient of 1. The aqueous compounds are definitely going to be diluted, and the gaseous compound is probably slightly diluted here. So what I can probably assume is that the reactants are being diluted a little bit more than the products are. So basically, this would mean then that the concentration of the reactants are decreasing slightly relative to the concentration of the product. And so letter B, I would probably expect this to shift left just slightly. Finally, letter C, add HCl. You should recognize that HCl, hydrochloric acid, is a strong acid, which will react with the base here. It will react slightly with the NaHCO3, which is a weak base, which we'll learn about a little bit later. But more importantly, it's going to react rapidly with the strong base. So if I add HCl to the system, that's effectively removing NaOH from the system. And if I remove NaOH from the system, the reaction should shift left in response. Okay, let's have you practice, let's have you try this practice problem. The reaction below has a delta H of plus 56.9 kilojoules. How will the amount of NO2 at equilibrium be affected by the following changes? So I would like you to pause the video and try these 5 questions. All right, let's go over the answers. If I were to add N2O4, this would cause the system, you're adding something on the left, system would shift right, and so we would say, you could answer it as system shifts right, or you could say more NO2 will be present. Increasing the volume of the container. So look at the number of moles here. We've got 1 mole of gas on the left, 2 moles of gas on the right. If I increase the volume, I decrease the pressure, the system will shift towards the side with more moles of gas, and so the system would shift right here. Lowering the temperature, well, let's look at our delta H value. Our delta H value is positive. This means it's an endothermic reaction. The system is absorbing heat. We can think of heat as a reactant. So if heat is a reactant and I lower the temperature, that's effectively removing a reactant. And so if I'm removing a reactant, the system would shift left in response. Adding a catalyst, your answer here should always be no change, right? Adding a catalyst does not shift the equilibrium. It just makes the system get to that equilibrium more quickly. Will any of the above changes alter the value of K? Remember that K, the equilibrium constant, just like lowercase k, the rate constant, is dependent on temperature. And so we'd expect then that letter C would alter the value of K, but A and B should not. All right, here's a little more practice with LeChâtelier's principle. Hydrogen gas is produced by the following endothermic reaction. CH4 plus O2 forms CO plus 3H2. Assuming the system is initially at equilibrium, indicate the direction of the shift if. Go ahead and pause the video and try these 5 problems as well. Oh, sorry about that. I thought the answers were given on my next slide there. If H2O is removed, the reaction answer for letter A, reaction would shift left. If the temperature is increased for an endothermic reaction, letter B, the reaction would shift right. Letter C, the amount of nickel catalyst is increased. So when you see something written over the arrows, this generally indicates that it's a catalyst. Remember, catalysts have no effect, so letter C, no effect. Letter D, H2 is removed. I would expect this to cause the reaction to shift right. And letter E, volume of the container is tripled. Here, I would also expect the reaction to shift right towards the side with more moles of gas. Okay, that's the end of this lecture. Here's 3 more practice problems for you to try. So if you would like a little more practice, I would encourage you to pause the video, go ahead and try these 3 problems. And the answers are given here. That's the end of this lecture. I hope you enjoyed and found this useful. As always, please feel free to reach out to me if you have any questions, whether it be via email or in the comments down below. I'll see you in the next one, and I hope you have a great day.